So we're going to be looking at the next little section, chapter 10 here, which is 10.3, which is on circles. Circles and sectors, to be honest. So let's review the following formulas that we have so far for the shapes that we know. So rectangle, square, and parallelogram, that area was simply base times height. Base, height, no big deal, all right? Triangle, we found out that a triangle is basically half of a rectangle, square, or parallelogram. So if I have a triangle here, I could draw another triangle like this and make it into a parallelogram. I find the area of the parallelogram using base times height, and then I divide it by 2 to get just the triangle I want. So that's where we got the formula of base times height divided by 2. Again, it's always good to remember the origin of these formulas. That way you don't, it basically helps it sink in better in your head, essentially. Because if you know where it comes from, there's also a chance for you just simply forgetting it. Trapezoid we got by, again, this notion of making it into a parallelogram. So we had a trapezoid here. We transformed it into sort of another parallelogram by turning it upside down, and found that if we get the area of this parallelogram and then cut in half, we get the trapezoid. But it's not simply base times height divided by 2 because it had two bases, one here and one here. It's just that this base now is on bottom, so we have to add them together. So we got the area is base 1 plus base 2 because that made the base of the giant parallelogram, and then times height and divide by 2. Or again, another way we put it is that it's the same thing as a triangle, but since the head's cut off, it now has two bases, so you have to add the bases together, whereas before you just had one base to worry about. And then for a rhombus, and this also is for a kite as well, so I'll put down here a kite. Remember, these are those diamond shapes like that. Excuse me. And in this case, we had two diagonals. We had a left to right and up and down diagonal, and we found that the area was just the first diagonal times the second diagonal times a half. And this again was due to the fact that there's basically four triangles in here, and each triangle has a base that's half of one diagonal and a height that's part of another diagonal. So if we put all four of them together, we end up with two full diagonals and then again times height, because these diagonals are basically forming the bases and the heights of those two triangles. So now we have circles and sectors to be put in here. So let's go ahead and start with circles. So again, some of you might already know the formula for a circle, and some of you might be able to guess it through, but it's helpful to know kind of how the formula for a circle is derived from, because again, that helps it sink in better. And this still deals with the notion of being able to cut it into shapes that we know how to do. So again, we're going to try to take this circle and cut it into a shape we know how to find the area of, because we don't know how to find the area of a circle by itself. So we have to figure out, okay, if we're going to cut the shape up, what's one of the key measurements for a circle? And pretty much the only key measurement for a circle is the radius. And the reason the radius is the key measurement is because that's one of the only measurements you can actually take. You can't really take the circumference measurement, although you could, like, tying a piece of string around it and stuff, but you calculate the circumference. Like, remember, circumference is 2 pi r. So you calculate the circumference by using the radius, and you calculate the area by using the other measurements, and you calculate the diameter even by taking the radius times 2. So really, the radius is the key measure because it's the one that you use to calculate everything else about the circle. You could argue the diameter is there as well because technically you can also measure the diameter too, but usually it's the radius that gets used in all the formulas because it's a smaller unit of measurement. Usually you want to use the smallest type of measurement you can use to be the most precise. So we stick with the radius. So because of this, the radius is going to play another key role in the area formula. So again, it's all about this radius. So let's again picture out how this comes into play. And I kind of diagrammed it out here, but just to kind of walk you through what's happening here. So we take a circle and we say, okay, can't solve for a circle. And usually in math, when you can't do something, the goal is to reduce it to a problem you've already done and then do that instead. So there's an old joke about that too, that there's a mathematician and he trains to be a fireman. And so he goes through fireman school, goes through all the training, and to test him, they set a dumpster on fire and they tell the mathematician, go put the fire out. And the mathematician go ahead and puts the fire out well and perfectly, and they're all good, and they say, okay, great, you're a fireman now. So later that day, a house gets caught on fire, and nobody's in there to make sure the joke is high school appropriate. So an abandoned house gets on fire. The fire truck goes, and the mathematician's there, and they say, okay, mathematician, go put out this fire. And he looks at the fire, looks at the house, it's burning, and he goes and lights the nearest dumpster on fire and then puts out the dumpster. And they look at the mathematician and say, what are you doing? He's like, well, I'm reducing the problem to something I've already solved. Because he knows how to put out a dumpster fire, doesn't know how to put out a house fire. So he's just going to set the dumpster on fire and put that out instead. Now, again, it's probably not the funniest joke because it's a mathematician, not a comedian. But that's the kind of same idea here, is that we're going to take this circle, which is our house fire, and try to cut it into a problem that's more like a dumpster fire that we can then solve. And let's go ahead and get off that analogy now because it's not really working. So we have this circle here. What we're going to do is cut it into slices. Now, you can make these slices as small as you want. I just did 8 here just because it's a little bit nicer to see when it's 8 slices. But you can make these, 10, 12, 50 slices if you want to. But we're going to cut it up into individual slices, and they're all going to be congruent. So all these angles are congruent, so all these slices are equal. Okay? So equal slices all the way around. And that still doesn't help us out, so what we're going to do is we're going to rearrange these slices. So half the slices, the shaded ones, I'll put a little shading, little shading in here. Half of those slices I'm going to put on the bottom, and half those slices I'm going to put on the top. And that means, again, in terms of the way they're facing. So 4 of the slices go where the point's pointing down, 4 of the slices go on bottom where the point is pointing up. Well, if you look at this, this very closely looks like a parallelogram. In fact, let me see if I can't match one up here. This is almost similar to, if I flip this around here, and we flip left and right, there we go. So it's very similar, not quite exactly accurate, of course, but it's very similar to a parallelogram. Now, I could try to manipulate this further and make this guy slant this way or not, but you can get the idea that it's very close to a parallelogram. Well, let's say it is a parallelogram. Because if we cut these small enough, if we made these slices very, very small so they were almost like just single lines, it would pretty much look indistinguishable from a parallelogram. So if this was a parallelogram, how do we get the area? Well, we know that the area is base times height. That's how you get the area of a parallelogram. Well, what's acting as the base here? Well, this bottom base, if I move away my parallelogram, there we go. So if we delete that, this base here is basically all these curved sections. This section, this section, this section, this section. Well, what do those curved sections represent? Well, they represent the circumference of the circle. They're these little pieces right here. They're the edge of the circle. But it's only half of them, right? Because 4 are on bottom and 4 are on top. So this base is basically half the circumference of the circle. That's all it is. You take half the edge of the circle, and those are what form the bottom of your little mock parallelogram here. And what about the height? Well, if you look closely, the height here, if we go from like right here to up, if we take that measurement there, or even like from here down, that's basically just the radius. Because remember, if I do that in another color here, each of these lines, that's a radius because these little points are kind of like the center of the circle, that they were originally at least. So that's a radius, that's a radius, but everything in between there's also a radius as well, because I could draw, okay, radius there, radius there, radius there. So splitting these slices in half is akin to just drawing another radius. And we know that all radii are equal, so this distance is going to be the same as this distance, is going to be the same as this distance, is going to be the same as this distance. So it fits the format of a height where the height should be equal throughout the entire shape, which it is, because all the radii are equal. So the height is no more than just the radius. So now we can kind of start making a formula here. The area of this parallelogram is base times height. Well, the base, we just said, is 1/2 of the circumference. And the height, we said, was the radius. So this could be like a formula right here. Area is half the circumference times the radius. But we really don't like using this word circumference, because circumference requires its own calculation. So you don't want to use circumference in the area problem, because then you have two formulas that are trying to intermingle, and that really doesn't work out that well. So what we can change this into is just write out the formula for the circumference. So 1/2 times, what is the circumference? Well, the circumference is 2 pi r. So instead of writing c, I'm just writing out the circumference formula times r. Well, we can even go even further now, because we know what 1/2 times 2 is. 1/2 times 2 is just 1. And 1 times anything is just itself. So this can just basically go away, because 1/2 times 2 is going to make 1, and since we're timesing by 1, nothing changes. So really, this is just pi r times r. Well, r times r, we know another way to write that is just r squared. R times r is r squared, just like x times x is x squared. And this is where we end up with the payoff here, that our area formula is simply pi r squared. And again, some of you might have known this already, but knowing kind of how it comes from and how it comes out, even if you don't necessarily fully grasp the idea, knowing that it has to deal with taking the circle, cutting it up, making it into a parallelogram, and then using the properties of a parallelogram to kind of whittle it down to a area formula for the circle, again, that might help stick it better in your head so you're not constantly trying to look it up or remember it. And if you notice, it's very similar to that of circumference. So area, remember, is pi r squared, and circumference was simply 2 pi r. So if you look closely at these formulas here, they're very similar. They use all the same numbers. It's just that in area, the 2 is the square, where circumference, the 2 is just the multiplier. So if you can remember one of them, you can remember the other just by moving the 2 to the appropriate spot, either moving the 2 down to make it circumference or moving the 2 up to make it area. The way I remember it is that area deals in square units, right? So square feet, square inches, square centimeters. So it should have a square in the formula. That's why we get the r squared, because it's square units. But again, very small, very simple formulas to use. So let's use them. Area of a circle with a radius of 8. Well, again, this is pretty simple if you want to draw it out. You have a radius of 8. Well, our formula is simply pi r squared, right? Pi r squared. So it's just going to be pi times 8 squared, or 64 pi yards squared. And if you want to multiply this out, you can. If you want to leave it at 64 pi, that's fine too. A little bit easier to grade that way, to be honest. As always, be careful when they switch it up and give you the diameter. So if they have a circle here, and let's say the diameter is 12, I know it's a really poorly drawn circle, but you'll have to go with me here. Well, we're not going to use 12. We're going to use the diameter, which is only 6. So it'd be pi times 6 squared, which would give you 36 pi feet squared, which again, you can multiply out if you really want to get the decimal. By the way, usually it's the number that goes first, then pi at the end, just like you normally write 2x rather than x2. It's the same concept here. Now, if you wrote down pi times 36, I'm not necessarily going to be that ticked off about it, but just know that that's conventionally not the way you write it. You write it with the number first and then the pi in the back. If you're doing your problem, that's fine if you write the number on the end. But when you get your final answer, that's how you conventionally write it. Now, this one's a little bit trickier because it says find the area of a circle with the circumference of 28. So we actually don't know the radius or the diameter, but we have to get the radius because we can't do the area unless we know the radius. So what you do is you fall back on what you know. Well, I know the circumference formula is 2. Whoa, let me try that again. The circumference formula is 2 pi r, and I know that the circumference is 28. Well, if this is my circumference and this is the formula, let's just go ahead and solve this equation. Circumference is 2 pi r. Well, 28 is 2 pi r. Let's go ahead and figure it out here. So in this case here, I want to get r by itself. So some of you might be saying, okay, well, you divide by 2 and then divide by pi. Because 2 is being multiplied, so you get rid of it by dividing. Pi is being multiplied, so you get rid of it by dividing. Well, if you're going to divide them both, just do them both at once. So divide by 2 pi and divide by 2 pi. Because what happens here is that these 2's cancel, these pi's cancel, and you're left with r. And then over here, you have whatever that's going to be, 28 divided by, make sure I put parentheses here. Make sure I put parentheses here because I want to make sure the calculator does 2 pi first. If you do not put parentheses, you will get the wrong answer in most calculators because calculators really don't do a good job of order of operation interpretation. So make sure you put parentheses around the 2 pi so you don't end up with a weird answer. And we get 4.46 essentially. So 4.46. Now again, that's not the end of my answer because that's my radius. I want to get the area, not the radius. So I need to go back and use this in my area formula now to actually get the area. So pi times 4.46 squared. And so let's go ahead and do this out here. 4.46 times 4.46, which is just the same thing as doing 4.46 squared. So if you want to write 4.46 squared, that's fine too. Times pi. Remember, multiplication can be done in any order. So I did this first and then times it by pi. Again, anything's fine. 62.491. So 62.491 inches squared. This one I actually did the decimal form just because if you already have a decimal already, there's really no use in saving the pi at the end, because usually you write it like this so you can avoid a decimal answer. Well, I'm going to get a decimal answer anyway for this square, so you might as well just do it all at once, right? So again, just be careful on what kind of question they give you. You always have to have the radius before you do anything with the area. Now, lastly, we have this thing about sectors. So sectors are basically a slice of a circle, or a piece, but we usually call it a slice. So it's a slice of the circle. Now, the sectors we're going to talk about are, I guess you can call them central sectors if you want a really big tongue twister there. Ugh, I almost twisted my own tongue. Which basically means that they have to be cut from the center, like a piece of pizza or pie. So if this is a pizza right here, and I said, cut me off a slice, you wouldn't go like this, because that's not how you cut a pizza unless you're really weird. A sector we're talking about goes from center to edge. So this is the type of sector we're doing, not this. Okay? So how do we get the area of something like this, where you just want the area, that shaded slice there, not the area of the entire circle? Now, some of you might be thinking composite shapes, like you find the area of the circle, you subtract some other area, and you get the area of the sector. And I would applaud you for doing that. It's a really interesting way of thinking about it. But we actually have a formula for it. And it comes from the fact that you're basically making a proportion. So let's say we have a circle. And let's say we know the following information. Here's our sector. What we need are the degrees of the sector. We need the radius. And that's about it. If we have how big the sector is in terms of degrees and we have the radius, we can use the following formula to find the area. Now again, it's not really a formula, it's more of a proportion, but same idea, right? What you do is you take the area of the circle over over pi r squared is equal to, no, sorry, that's not the area of the circle. Let me backtrack here. I should probably still put a there, but this is, actually, yeah, let me use capital A. I'll notate it in a second here. So this is area of the sector. So right here is area of slice. I should say sector, but I'll say slice just to make it a little bit easier to understand. So area of the slice divided by pi r squared is equal to the degrees over 360. So this is usually your x. So this right here is usually your x part of the formula, because this is what you're trying to find. You're trying to find out how big the area of the slice is. And again, if you notice here, it's just like a conversion almost. Area of slice, area of circle. Degrees of slice, degrees of circle. So slice, circle, slice, circle. Piece, total, piece, total. So again, don't try to memorize this, bootstrapping it by just thinking, okay, a over pi r squared equals d over 360. A over pi r squared equals d over 360. That's one way of doing it, and that might succeed. But if you want this to stick for now and ever, then again, kind of figure out, okay, why is this happening? And again, the reason it's happening is because you're comparing apples to apples each time. Area to area, slice to piece. Angle to angle, slice to piece. These should change in proportion. As the degrees get bigger, the area gets bigger. Think about this as, this is the percentage of area you have. This is percentage of degrees you have in your slice. These two should factor out. The degree percentage should be the same as your area percentage. So if you know your degrees, and you know it's going to be out of 360, you can say that this fraction here, which is your degree percentage, should be the same as this fraction here, which is your area percentage. But again, it all comes down to area, area, slice, whole, degrees, degrees, slice, whole. And you just cross multiply to solve it out. So let's take a look at one. Area sector, there's a 40-degree angle and a radius of 10. So let's draw it out here. So boom, boom. Oh, that's really ugly. Let me even try that. Actually, I have a tool here, don't I? Let me try be productive here. There we go. So that's a nicer circle than I could ever draw. So circle here. We have a slice. Slice. That's a really bad lines, I know. 40 degrees. And it says radius of 10. 10. There we go. So how do we get this out here? Well, let's go ahead and set up our proportion. Area of the sector. Well, we don't know that, so we're going to put a big fat X there. Area of a sector. Down below, we have pi r squared. So pi 10 squared. So again, pi r squared, because again, this is the area of the full circle. So area of the sector, I don't know. Area of the full circle, I do. Degrees of the sector, that's 40 degrees. Degrees of the circle, it's always going to be 360. Now, for the more intuitive among you, you can always reduce this fraction before you cross multiply, by the way. So for example, if you're inclined to, you can say, oh, well, these zeros cross out, so I can make it 4 over 36. And even 4 over 36 I can reduce, right? Because I can divide them both by 4, because 36, if you don't believe me, 36 divided by 4 is 9. So this is basically 1 over 9. 4 divided by 4 is 1. 36 divided by 4 is 9, is equal to x over pi times 10 squared. And then you can cross multiply this fraction, which is a little bit easier. Now, just because I know some of you won't, let me go ahead and do it the more difficult way, just so I can have a baseline there, and then those of you that want to shorten it up, you know how. So, cross multiply here, cross multiply here. This is going to be 360x. Over here, we're going to have 40 times pi times 100, which is 1256.6.37. So 1256.6.37, which seems like a big number, and it is, but remember, we're going to divide it by 360 anyway, so it's going to be cut down by quite a bit. And we get x is equal to, so this divided by 360, we get 34.9. So 34.9. And that's the area of the sector. So again, it's more about proportions than subtracting areas or whatnot. And that's how we solve it. So remember, slice over whole, area over area. Slice over whole, degrees over degrees. This last one here is the same question, but it's just worded differently. So it says a circular pizza is cut into 8 equal slices. Pizza has a diameter of 16 inches. What's the area of one slice? So once again, let's go ahead and diagram it out by actually making a nice circle and nice straight lines this time. So we're going to cut this into 8 slices. So 2 slices, 4 slices, 6 slices, 8 slices. Who knows, cool math games would help you out here, right? There we go. So 8 equal slices, 16-inch diameter. Well, if it's a 16-inch diameter, and that last line is really off, it's bothering me. There we go. If it's a 16-inch diameter, that means the radius is just 8 inches. So each line here from center to edge is 8 inches. So the full line is 16. This line right here is 8. Now what we're missing is the degrees, right? Because if I go to set this up, I have area of the sector, x, over pi times 8 squared is equal to 360 on bottom, but I don't have any degrees to put on top. I don't know what this is supposed to be. Well, the key here is that it's 8 equal slices. So these angles should all be equal. And if I know that the full thing is 360, that means one of these angles, since they're all equal all the way around, one of these angles is simply 360 divided by 8. So 360 divided by 8 is just 45. So each angle is 45 degrees, because I simply take all the degrees in the circle, divide it into 8 equal pieces, and I get 45 degrees for each slice. Now again, those that are more intuitive among you might be able to figure out a way you could actually shortcut this by using the fact that it's 8 equal slices and figure out what this fraction would be, but I'll leave that to you if you really want to. So now we just go ahead and solve it like we did before, cross multiply. So cross, cross, get 360, try that again. 360x is equal to, and let's go ahead and do our calculator here. So pi times 64 times 45 gives me 9047.79. 9047.79. And then we divide by 360. So divide by 360. And we get 25.13. So 25.13 is equal to x. Whoops, a little close cut there. Let me try that again. There we go. So again, sectors aren't really that big of a deal as long as you know the area of a circle, because you need to know that for your bottom piece there. But it's all a matter of setting up that fraction. And we did this very similar thing with arc length, if you don't remember. When we tried to figure out what the arc length of something was in terms of linear units, we had a very similar fraction, except we used circumference rather than area. But it was the same idea almost. So again, everything kind of relates to each other here in geometry, especially with circles. Circles are very circular in their logic, not to be punny. Well, actually, yeah, to be punny. Circles are very circular in their logic. So everything kind of ties back to each other. That's it for this one. Hope you helped you out. Let me know if you have any questions. Have a good day.